Well, thank you very much, Dean Echeria. It is indeed a privilege to be here at this really successful meeting. My congratulations to those who were inspired to create this meeting, and more importantly, those who invested an enormous amount of time to organize this. And I'm absolutely delighted to be here. I'd like to also mention that I will be speaking very quickly about a lot of work that's being done here at Indiana University, and equally importantly, the context at the national scale in which it's there. I'd like to mention my colleague, Professor Martin Swaney, who through his leadership both at the Center for Research in Extreme Scale Technologies and in the new Intelligent Systems Engineering department is responsible for much of the progress being made both on the educational and the research side here. You're looking at reality shiver. A year ago or so, for the first time in the history of mankind, we were able to detect, analyze, and demonstrate the success and correctness of the Einsteinian equations by watching an event that occurred more than a billion years ago. Let me just put that in context. That was so long ago. Life was so primitive. Most of it was Republican. Oh, no, I wasn't supposed to say that. Sorry. Okay. So this is really back in the Precambrian period. This was a result, and we really hit it out of the park. This is two black holes colliding with each other, converting about 3 solar masses almost instantaneously, a matter of milliseconds, into pure energy, and essentially all of that energy released as gravitational waves. This is an extraordinary event in the discovery of science and the confirmation of one of the most important models that we understand. Now, there were two classes of tools that were applied to this extraordinary achievement. One, and I should say one class, but in two different instances, was the LIGO, or Laser Interferometric Gravitational Wave Observatory, one in Louisiana and one in the state of Washington. Each of the legs is about a mile long in both of these tools. But this is not the first time that the interferometer has revealed much of the true nature of science. In fact, perhaps one of maybe the most important science discovery never made was achieved in 1887 by two scientists, Michelson and Morley, when they spent many months using, at that time, the most sensitive interferometer floating on a bed of mercury at Case Western Reserve to measure the ether. Now, the ether was hypothesized as, of course, the medium through which the then assumed wave phenomena of light propagated. Now, as everybody in this room knows, it's a good thing they didn't find it because it's not there. Michelson was never happy with this result, and Morley died not long after of mercury poisoning. So not a happy ending. But I said that there were two classes. The second class is the supercomputer. Without supercomputing, this discovery would have been impossible. This is just a small part of the computing facilities that were applied, not just to the analysis of the data, but to the modeling and simulation of different classes of phenomena that were anticipated or predicted to be able to produce gravitational waves. Essentially, the computers produced the signatures, the templates of what this phenomenon should look like, and then against real data. You've got to understand this incredible data. We're talking about a perturbation less than the size of an atom against a mile-long measurement chain, and to discover that and to extract that signal from an enormous amount of noise. I could stamp hard with my foot here, and there would be some residual effect on LIGO in Louisiana. And so this is extraordinary. Now, This is only one of a number of fundamental discoveries which have been attributed. About three and a half years ago, at the Large Hadron Collider, the discovery of the Higgs boson, which is purported to provide the property of mass for at least the 5% of matter that we understand in the universe. The other 95, we haven't a clue, apparently. Oh, we named them dark energy, dark matter. We don't know what they are. And a third discovery, more than a dozen years ago, again, using supercomputers, was not to prove a theory that we already had, but in fact, completely blew us away, surprised us. We wanted to understand how, and forgive the terminology here, how fast the slowing down of the universe was. Surprise, wrong question. It isn't slowing down, it's accelerating. We didn't see that one coming. Again, supercomputers allow us. Now, the field of high-performance computing really enjoys measuring itself. It likes using a form of test which is very friendly, allows us to look good. And we use a program called the LINPACK benchmark by my friend. A number of people contributed, led by my friend Jack Dungara and colleague at the University of Tennessee at Knoxville, and also closely associated with Oak Ridge National Laboratories. Jack is among the world's expert at doing linear algebra by computers, in particular dense linear algebra. And for over 24 years, the field has been measuring itself to understand what the number one machine is. We look a lot at that, but also to understand the top 500 machines. And with that fact, somebody cleverly referred to it as the top 500 list. That took a lot of effort. Jack and others have been tracking this data and watching over multiple generations of technology development as the delivered performance, at least according to this metric, has shown that in the time of measurement, the performance has gained by a factor of 1,000,000. Now, please come back and tell me another technology that in 20 plus years has improved by a factor of 1,000,000. And you know, that's the easy part. The hard part is in the lifetime of a single individual, and I hesitate to say, but my lifetime almost exactly, the field of high-performance computing, which is the field of computing, has increased conservatively by a factor of over 10 trillion. And yeah, in between 1,000,000 and 1,000,000,000,000 is 1,000,000,000. So there's another factor of 1,000,000 or more just sitting there. This is unprecedented by any measure in the history of human technology. Now, this chart is a little misleading. The red line is the number one machine, and it's pretty seesaw. You get the sawtooth kind of curve. A really big machine will be built, and nothing will catch up to it. Each of those dots represents 6 months in evolution. The yellow, brown, orange line at the bottom is the number 500 machine, mostly a little bit flatter, a little bit smoother. You'll understand why in a minute. The impression you would take away with this is that, well, it's distributed throughout that space in between. By the way, the blue line is the sum of all of the 500 machines. My colleague at Crest, Dr. Maciek Brodowicz, did an analysis I asked for using a linear regression techniques to examine the hypothesis that we're really not looking at a uniform or homogeneous distribution of machines, but that we have really a much simpler distribution. As you can see, that's the case. More than 90% of the machines are in that almost horizontal line that you're looking at. Only a very few of the machines are as much as 10 or more times, almost 100 times, in fact, the average of that large body of set. And then there is a small range of transitory machines. So when we talk about supercomputers, we should not be talking about who has the fastest machine. And by the way, I'm about to talk about who has the fastest machine. But we should talk about the science being performed and accomplished through large numbers of still very high performance machines throughout the country and internationally. Now, okay, the big fast machine. So in supercomputing, the big elephant in the room is, well, I need a big elephant there. Oh, no, don't laugh. This is actually apropos. I took this picture. And more importantly, one of our important collaborators with Indiana University, under the auspices and funding of the National Science Foundation, is the Texas Advanced Computing Center, who happened to be driving the vehicle in which I was sitting. Let me be more specific. He was learning how to drive in reverse at that moment. I don't know how many of you speak elephant body language, but he is not smiling. Okay. This was, in fact, I gave a presentation in South Africa. This was a couple of years ago, and at the Center for High Performance Computing. It's really, really wonderful to see the accomplishments. And in fact, TAC had donated some used hardware to the CHPC in Cape Town, which is being used both for some science and for education. Here's the animal. This is the Sunway Tai Hu Light, and that's an approximate pronunciation. Please don't quote me. This machine was only recognized as the fastest machine in the world as measured by LINPACK. And anybody who understands statistics will appreciate it when I say this is a self-sampling set of machines. Which is to say only those who want you to see their numbers show them. This is the first of these machines that in peak performance exceed 100 petaflops and which have a fairly good efficiency, according to LINPACK, of over 70%. That's the good news. I don't want to take any credit away. Another actual aspect of the Chinese machine is that they built the chips. This is a significant accomplishment and should cause others in the international community to pause. Nonetheless, there are other aspects of the machine. While they have over 100 petaflops, 125 petaflops peak, they only have about 1% of that in terms of memory capacity. That's about 1.3 petabytes. This is a big difference. When I was young and growing up, a long time ago, we had a rule of thumb. It was, I need 1 byte of memory for every flops, notice S, every flops of performance. And now we are at 1/100th of that. The second is, I've been speaking about the HPL, or LINPACK benchmark, but there's another emerging benchmark called HPCG. The CG stands for conjugate gradient, also related to linear solvers. And in this case, the efficiency is not 70% plus. It's less than 1%, actually something on the order of 0.3%. But the deeper question is that class of measurement, is that metric of any value in itself? Are we in fact measuring the wrong thing? Because truthfully, the real value is time to solution, and the science or the societal good being performed by the computing. Now, these breakthrough machines have occurred not once, but many times throughout the history of computing. Here's a chart. It doesn't take us up to today. It's the first 60 years or so, where the performance back just after, well, no, I'm sorry, during World War II, an electromechanical machine developed by IBM and at Harvard, the unimaginatively named Harvard Mark I, produced a throughput of 1 ops. That's operation per second. Remember, we're now talking about billions of ops, literally approaching. The technology changed. Many of you know this story. We went through generation after generation of technology, from electromechanical to vacuum tube, from vacuum tube to transistor, from transistor to small scale integration, medium scale integration, large scale integration, yes, one more, very large scale integration. And as a result of that, about every decade, the achieved performance rated about a factor of 200 or so. It obviously changed. 200 every decade. And this is extraordinary. But it wasn't just we got it wrong at the beginning and suddenly we got it right. It was a steady, persistent pervasive progress through a combination of technologies, computer architecture, algorithms, and methodologies of programming. When the top 500 list was first started, and this was 1993, 1994, in February of 94, I had the pleasure to participate in a workshop, a focused by invitation only workshop that was developed here. This was one of 4 working groups, a working group on architecture, on high performance architecture. The purpose of the workshop was to understand directions and therefore help guide and set directions for, well, funding for the development of petaflops architectures. Now, we're there. I mean, literally, we're there. Just walking distance from here is a really nice petaflops plus machine. I hope many of you have seen it in our data center. But at that time, the performance was 1/10,000th of that we were receiving. The gentleman in the tie, it was Seymour Cray. And Seymour Cray, his name is synonymous with the idea of supercomputing. Sadly, he passed away in 1997. 2 of the gentlemen off in your upper right there are both holders of the Seymour Cray Award. One as a father of something called processor and memory architecture, and the other for multi-threaded architecture. This is a very high-powered group of people. And yes, I was there too. It's pointed out that I had just as little hair then as I do now. It usually said, you look as young as you did then, which is to say, I then looked as old as I do now. I could go and I could give you the story on almost every person in that picture made a major impact on that. So Martina asked me to mention, and one of those was me. Not by intent, it was an accident, but these things happen. The Beowulf project was started by NASA in the end of 1993, and by the middle of 1994, we had implemented the first, what would become a commodity cluster, Linux cluster, PC cluster. We didn't invent clustering. We certainly didn't invent PCs. We didn't invent Linux, but we almost did. Linux sucked. I certainly didn't want to use it. It was some graduate student in Finland. The student had sent out some really garbage code on the internet, and whenever you send out garbage code, that attracts a lot of young people. I don't get it, but it did. One of the biggest impacts of this project, which was only supposed to last for 2.5 years or so, was that in order to make a cluster work at all, we had to make the networks work. In order to make the networks work, we had to write the networks drivers. And my colleague, Donald Becker, wrote what became essentially all of the Ethernet network drivers, and this lasted for years and years. And most of the network drivers today are derivatives of the work that Don created, and as a result made Linux a real operating system. Today, more than 95% of all supercomputers run Linux. I'm not taking credit. I'm just saying it happened. This is also taken from the top 500 list, and this shows the different classes of architecture that were on the top 500 list. The light blue down below is MPPs, massively parallel processors, a good example of which, again, is sitting over in the data center. Lovely machine, a Big Red 2, becoming Big Red 2 Plus. This large orange blob, those are clusters. Commodity clusters exceed 85% of all of the systems on the top 500 list. But the real message here is that different classes of machines at one time or another made significant contributions to supercomputing. Technology, architecture, programming, algorithms are constantly changing. They're changing in how they approach and exploit the advances made, but they are not changing in terms of fundamental problems that they're addressing. The amount of work they have to keep their hardware busy, the time it takes to move something across the system, the latency, the amount of extra work it takes to control both the physical hardware resources and the virtual software resources, and then well, things bumping into each other, whether it's for memory or for networks and so forth. Here's an instance. We ran this data. This is an example of, about 128 cores, not a big machine, running a well-known code called Gadget. It's an n-body code, also supports something called smooth particle hydrodynamics in various simulations. Red means we're doing useful work. Blue means we're not doing useful work. Doesn't take a computer scientist to say red good, blue bad. This is a typical form of execution pattern, guaranteed to make sure that the computation progresses at the slowest possible rate. Now, there are codes in which, because of their uniformity, the regularity, that they would be mostly red. And guess what? LinPack is among those. These notions, and let me just show you one other. Here is an analytical model of one of those factors that I mentioned, this one overhead. It is so normalized as to have absolutely no meaning in any actual number that you can use. But again, you don't need numbers to understand the trend. Every one of those lines is flatlining. Independent of the amount of hardware that you throw at a problem of fixed size, you're not going to get more than a certain amount of percentage determined by the overhead, which is a property of the system you're using. This is a fundamental challenge to advancing effective computation. These problems have certainly been understood, and with the Chinese, and I'm not saying this is the reason, but it is a fact, with the Chinese not only having the fastest machine, for the last 3.5 years, but actually having more machines on the top 500 list than the United States does or any other country. We recognize that we are in a competitive situation where all of the fields of science and engineering, industry, commerce, and society are dependent on the availability and the capability of the machines that we have in this country. And when we are not pushing the edge of the envelope due to, well, may I say so, political problems, we are not just not moving forward, we are relatively moving backwards. It is not all bad news. Here, for an example, is a block diagram of the new chip, Knight's Landing, coming from Intel, moving away from the classic Xeon processor that many of you have in your laptop where you're currently reading your email while I am speaking. Oh, I'm not sensitive. Providing far more processing capability on a die than we ordinarily have. And not far from here, just across the border, in 2018 will be deployed a machine in excess of the capability that I've described in the Sunway system in China, using these new chips. In fact, this is only one of 3 machines that will be deployed. The 2 others, one at Oak Ridge National Lab in Tennessee and the other at Lawrence Livermore National Lab in California. However, these are different forms of machines that I'm speaking of. Now, let me pause because I'd like to begin to transition to where Indiana University is, and if not the unique, at least the important contribution that IU is investing in and making happen. And I need to ask my hosts, you have carefully not positioned any clock, so I have no idea how I'm doing on time. It's a very strange thing. When I'm sitting where you're sitting, time moves so slowly. And when I'm standing, it's like zoom. I'm sorry? More or behind me? Okay. Either way, I'm in good shape. All right. So this is where my no nonsense factual talk ends, and I now move into a more editorial, subjective, opinionated viewpoint. At every one of those points of singularity that we have experienced over time, it's been a paradigm shift. I know that's a cliche, but there's really no other way to talk about it. a fundamental change in the opportunity that presents itself is adopted and exploited and moves us. Oh, this is great. There are 4 digits, and I have no idea what they mean. They're counting down. Now, in many movies I've seen, that means at the end of this, something explodes. Right? That can't be right. We are in a position, and it's curious, a field that is the most aggressive, as I've described earlier, is one that is also proving to be the most conservative, the most entrenched in technology. It's sort of like the civil engineering of electronics. We build bridges now the way we built them then, and they fall down in a certain amount of time. The gentleman in the lower right-hand corner is John von Neumann and Robert Oppenheimer. John von Neumann, many accomplishments, and to which we associate the name for the class of computers that we develop, either directly, the von Neumann architecture, or derivatives thereof. Robert Oppenheimer led the team that developed the atomic bomb at Los Alamos. In this instance, they're both at the Princeton Institute for Advanced Sciences, and they're standing next to a computer that von Neumann had built. Some people appropriately say that this was the beginning of the von Neumann age. In fact, like so many projects, it took too long to go on, and by the time it was implemented, it was obsolete, meaning no disrespect to one of the geniuses. But von Neumann, in the von Neumann model, and we call it the von Neumann architecture because he wrote the seminal paper. So for those young faculty here, publishing matters. Von Neumann was on a train. He was heading west to Los Alamos from Pennsylvania, where a large electronic calculator called ENIAC was being developed, and for which he was consulting. And on that train, he wrote the paper, and he basically finished it, but he ran out of time. He got his name on it, but he forgot to put Eckert's and Mauchly's name on it. So they never got credit for the architecture that they contributed to intellectually at least as much. And if you were in the field of computer architecture, you didn't want to win the von Neumann Award. There isn't one. You wanted to win the Eckert-Mauchly Award. Nonetheless, in that were some assumptions that either directly or implied that certain things cost a lot more. The precious resources needed to be optimized for, such as the floating point unit. Now, I'm misspeaking slightly, because the floating point unit at that time was so expensive, there wasn't one. But any arithmetic logic unit at that time was very expensive. And so the architecture was designed to maximize the utilization of the arithmetic unit. The way to do this, according to von Neumann, was to have a register we call the program counter or the instruction pointer and issue an instruction at a time. Today, in spite of the fact that you may have 10 million different processor cores, that's how many cores there are approximately in the Chinese machine, they're still basically von Neumann architectures. Little tweaks, little optimizations, but they're still von Neumann architectures. There are a number of other assumptions as well. We don't even question these assumptions, and yet they are fundamentally wrong today. They were right 25 years ago. Today, they're absolutely wrong. Yet, we insist, due to legacy, due to heritage, due to inertia, if you want to be polite, call it momentum, we continue to make incremental changes of those architectures. And as a result, frankly, if you recall the roll-off on that, the advance of computing is slowing down. And it doesn't help that the speed of light hasn't gotten any faster. It doesn't help that atoms haven't gotten any smaller and therefore more dense. And by the way, Boltzmann's constant, they call it a constant for a reason. And for all of these factors, we are hitting a number of barriers that do not allow us to continue to exploit the technology advances that we had before. There is one opportunity that we still have. It's architecture. That is to say, how we design and build these computers. And a good way not to do it is to continue to make derivatives of von Neumann architectures. One of the things that changes the way we think about computing and is really important is that we have principally, throughout the last 60 plus years, written a computer program, compiled it, loaded it, and then let it do what it was going to do. We had already made essentially all of the decisions that were going to guide its evolution of the execution. In some cases, that is perfectly fine. It's satisfactory today as well as it was 40 years ago. In other cases, it's a very bad thing. Think of the cannon down in the lower right-hand corner. I've actually seen this cannon. I think it's in Moscow. It's in Russia. I could be confused. It could be St. Petersburg. It's really big. The mouth of that cannon is like 1 meter in diameter. What's even more amusing is that the cannon balls, which you see down there, they're bigger than 1 meter. This cannon was actually never successfully fired in anger. Or even for 4th of July. Well, the Russians won't do that for 4th of July. But the point, the metaphor here is that of a ballistic approach to computing, as opposed to in the upper right-hand corner is the missile, the guided missile, the idea that you're constantly tracking your trajectory and making incremental changes of control in order to maintain your direction, whether you're going into orbit or you're going to hit a target. And so one of the important opportunities, truly a game changer, is moving from the static notion of compiler-driven computing to the idea of including a piece of code that operates during runtime and monitors introspectively what's going on in the hardware, what's going on in the software, and makes adjustments of the way the two are interrelated. And one of the things that Indiana University is leading in this country is in the area of execution models that empower the use of runtime system software. Now, I'm not going to bore you with the details. You're just supposed to be completely awed by this diagram. I mean, come on, squiggly lines, how can you go wrong with squiggly lines? But what this does is it pictorially represents an alternative approach to the control of the computation on the hardware during the runtime. It exposes much more parallelism. It allows you to reduce the amount of overhead that's being imposed. It allows you to adapt around the possibilities of contention bumping into each other, and it allows you to hide or even eliminate parts of the latency. We have modeled this particular class of computing using, in this case, some queuing simulation models. This particular diagram done by my doctoral student, Danny Kogler. Without going into details, it's pretty clear. There is a plateau, a pretty insensitive plateau, where you want to be, more is good here. And then if you happen to walk or move too much in any one of several parameters, you go over cliffs. You go right over the edge. How do you know if you're about to go over the edge? Well, if you did it by compilers, you don't. If you're following it by runtime, you do. This is just one example, one demonstration of the value of considering doing active, intelligent, introspective computing. At the Center for Research in Extreme Scale Technologies, a number of my colleagues have worked together to develop such an experimental runtime system called HPX, or specifically HPX5. This is runtime software. Now, if you're reading the fine print on the boxes, you see things like processes and parcels. Processes are execution stuff and spaces. Parcels are those long arcs that move work to the data. Typically, you only bring data into the work. We and others, I don't want to take credit as being unique in this, but in terms of some of the exploration, we are in fact at IU among the leaders. One of the important behaviors is how such a computational model or methodology interacts with the low-level fabric of the network. And in this is where Martin Sweeney is taking leadership and changing the transport layer and the underlying low-level hardware architecture, along with a number of his colleagues and students, to improve the quality of behavior in ways that we do not typically or ordinarily pursue. I'll come back to network in a moment. Now, the motivation is simply to develop a runtime system which is running, which has been used on any number of projects in the past and currently, is to improve the scalability, to improve the efficiency, to use it as a test bed to understand and conceptualize future architectures. To do so not by just thinking about software hacks that you can in an ad hoc fashion put together, but within the context of a conceptual execution model, that paradigm I talked about before, that thinks about all the layers of a computer at the same time. Curiously, we really don't know how to have that kind of conversation. We don't have the vernacular, the lexicon that actually lets you talk about a complete computer. You can talk about a compiler, an operating system. You can talk about an architecture, network, but you can't talk about them all at the same time. An execution model allows you to do it, and the parallax execution model, which is admittedly an experiment, allows us to consider all the pieces together, which also influences the programming models, helps drive the research at Indiana University, and adjust to something that's becoming increasingly important, the randomness of the behavior of the computing and the data movement and the data placement that we jumble up in one topic called asynchrony. We've discovered, this is just one plot from Danny, we wanted to measure, okay, what are the overheads for these things? After all, if we're going to consider possibly using hardware to support this, we need to know what the limits of the software were. Our discovery is we expected one bar there. As you look at this, and this is the overhead for switching two different activities that are going on concurrently within a machine, we find that, in fact, depending on conditions, the time it takes to do this context switching can change by as much as a factor of 2. And in this situation, a factor of 2 is a lot, especially when you expected one bar, one cost. This is driving our thinking very differently. Now, I realize I should show you, and let's see if this works. There we go. Let me push this button. That didn't work. Let's push it again. There we go. All right. This is a simulation. The algorithm is the class of wavelets to do adaptive computation. This is a simplified version of a star blowing up. There are actually two shock waves that come through. The key idea of multi-resolution is that you in this data set, you only put a lot of data points where you need them at the moment. And the light blue line where you see turbulence emerging is an example of this. So you have two shock waves, one crashing into the other, and you're able to do as little as 1/10,000th the number of operations that you would have done if you had the finest resolution for the entire computation. You can imagine how that would be significant. All right, here's one other, also done by Matt Anderson, who is also, I should say, also a lecturer at the Intelligent Systems Engineering Department. Now, in this diagram, what you see on your right, this is real world, okay? So you can get your hands, well, it's hard to grab a cloud, but these are real clouds that show a phenomenon known as Kelvinhelmholtz instability. And again, an HPX implementation using adaptive methods. There is a symmetry that's real there, and you can see where the very fine-grained turbulence and the flow, the same curvature that you're seeing in the real pictures, is occurring there. Now, I don't have a movie of this, but I would like to identify one last application, and this is brain science. I mean, really, brain science. With our colleagues in Switzerland and Geneva at EPFL. We are contributing to an experiment to try to make better brain simulators using these dynamic adaptive computing methods. Indeed, up until last week, we had a visitor, a doctoral student from EPFL, spent 6 weeks visiting CREST, implementing a simulation that they have in old school conventional practices and having it work successfully using the HPX runtime system with very favorable results. I don't want to leave you with the impression that an HPX implementation wins for every application. In some cases, frankly, the applications are well suited to the conventional practices. And then we're lucky to break even. We spend more time trying to do that than actually the useful work. I'd like to also mention that I've already talked about hardware and the potential opportunity of hardware. And we here at Indiana University are the only academic institution in the country to have deployed a small test bed of a special machine that is different because of the nature of its network. Earlier, I talked about the importance of network. I talked about the work that Martin is involved in heavily. This is one in which a topology has been developed that avoids any contention within the network. Now, it's unclear to what degree and under what circumstances this, I'll call it revolutionary topology and distributed control, how important that is across the spectrum. But for certain classes of computations that require fine-grained, that means very small messages, it is considered as potentially important to have a very different form of network than the very heavy-set networks like Ethernet or InfiniBand that we use now. The jury is still out on this. This is not a claim of fact or conclusion. It is a question to be answered, and we here at IU have the opportunity. But curves like this, provided by others, show, for example, that with very lightweight messages, this red line has a delivered much higher total bandwidth, useful bandwidth, than more conventional practices. In this case, the gray lines are different circumstances with InfiniBand. This opportunity to explore the possibility is, well, in this case, I can say unique to Indiana University with my gratitude towards the leaders. All right, so as I come to a conclusion, before the bomb goes off, we, in part because of the challenges and the methods I've already discussed, and because of the new Department of Intelligent Systems Engineering, are now moving our focus, our target of interest to a significant degree, no means by majority, as well to hardware architecture, something we haven't done outside of the networking area, something we haven't done a lot of. We're very excited about this possibility. The use of field programmable gate arrays gives us tremendous opportunity, even with modest facilities such as what we have at Crest, to explore and potentially change by order of magnitude some of these parameters that we're now measuring, that we're now experiencing, in order to make it possible to exploit these runtime systems. So my closing comments. Runtime systems are, in fact, only part of the total system hierarchical structure, but they are a significant departure from conventional practices, and we at IU have the opportunity to lead the nation, and in collaboration with other universities and national labs in this area, as we have done over the last few years. They must be derived and defined in part by support for and interoperability with the programming models, the compilers, the operating system, and the processor core architecture. So no one single layer is sufficient in and of itself to make the dramatic improvements that we in this nation need, that are in fact essential if we're going to move into the exaflops era. And therefore, I emphasize here that the architecture will have to be designed not simply to be incremental changes of the von Neumann architecture that goes back to 1950 and earlier, but rather to respond to the opportunities and the needs for runtime systems, new programming models, and most importantly, the new applications that will be so important to national security and to the national society requirements as a whole. Thank you very much.